G'day everyone, how you going? This is actually take 2 of the video. You can see that I've already done a bit of work here with circling things, and I made a bit of a mistake. I had a wrong number here, it wasn't working out, so let's go again. I'm doing inset method here, so what I'm looking for when 2 vectors are going to cross over. Now I might want that to happen, I might not want that to happen. Here's one example where I do want it to happen. This is you floating in the ocean. Imagine this plane is the flat ocean. This is you floating, and I know that the wind and the current is going to push you in this direction. Okay? But I've also got a mate over here in a boat. I want to tell him where to go. So if I just tell him where you are now, by the time they get there, you've already floated off. Okay? So I actually want the 2 of you to collide, so to speak, so they can rescue you and take you home. But here's a situation where I don't want them to collide. Here's harbour A, here's harbour B. Okay? 2 ships are leaving those harbours off onto their destination. You're working here in this harbour and you send your boat out on that direction. I'm working over here and I send my boat out. Well, we've got to chat so that we know they're not going to collide. Either your boat needs to speed up to get past this point, or slow down, or my boat's got to do the same. Okay? But one way or another, we've got to make sure that we pass that point at a different time. So what are we doing? Well, here's these two vector equations of a line, a start point and a direction that they're heading on. So I'm going to equate the i's first. So I've taken these ones that are circled and I've put them in there. On the left-hand side here is these 2, but I've dropped out the I part. I don't need that because I've already said that's what I'm working with. And here is the I part from the other one, and you can see I work that through and get lambda equaling 3. Now what that means is after 3 units, let's call it time, hours, after 3 hours, the I component is the same. Now remember we measure the I component here. So that means after 3 hours, in a horizontal sense, they will line up. Okay? But they could be here and here. So they're lining up vertically after 3 hours, but that's not necessarily that they're going to collide. So we've got to work the j's as well. So let's do the j's. So we've got -2 plus 1. And we've got 1 plus 1. Now hopefully this works out this time. Oh, I've already made a mistake, I can tell. What have I done? Oh, I missed the 2 here. -2 plus 2. So I think that will fix us up. Hopefully, yes, I think we're okay now. Yes, we are. So if I move this one over to here, 2 minus 1 becomes just lambda. And -2 over there becomes positive, becomes 3. So now because this one, the j's, and this one, the i's, are both giving the same answer, this situation that I described before can't be the case. Because in this situation, this one in the black, the j component of both ones are different. So the only time when this can result is actually right here because they line up in the i's and they line up in the j's. So when you solve something like this and you get the same answer for lambda in both i's and j's, that means that these 2 particles, ships, people, whatever, are going to collide. Now if I want to find out where they collide, I can take this lambda equals 3, put it back into either one of the equations, and just like doing linear equations, you've got to get the same answer out of both, because otherwise you've done something wrong. So taking 3, putting it back in here, that would find me that point right there, the collision point. Okay? Now you might say, well, if this is okay, I kind of get where I'm going, but isn't there an easier way to do it? Well, not an easier way, but there's probably an easier way to write this. Okay? So let's have a look at this. I'm going to write that RA with vertical coordinates. So I'm going to write it like this. I'm going to go 1 minus 2 plus lambda lots of 1 and 2. So can you see how that's going to be RA? Therefore, RB is going to equal, same idea, it's minus 5 and 1 plus lambda lots of 1 and 1. No, 3 and 1, 3 and 1. What am I doing? I'm not doing so well today. So that might be a little bit easier for you to see because there's no I's and J's in there. We recognise that the top is the I and this one's the J. So if I wanted to write these equations, can you see how that there gives me this here? That there gives me this here. So I just equate the top line part of it and I get the first one, and then equating this one and this one gets me here. So you might find it handy to write it in this format because you can kind of see what's going on a little quicker. Now, a little extra here, 3D vectors. Now, this works if you're floating in the ocean, sending ships out or something like that. But what happens if you're flying aircraft? Well, then we need a third axis, our IJK axis, coming out of the board because that would be the planes taking off. Okay? Now, in that case, you'd have to do a third equation. And if you want them to collide, which in the air I'm not sure why you would want to, well, a missile perhaps, then your IJ and your K has to be the same for it to work. And then again, you could substitute it back in and you could find when that happens. Okay? I guess that's the idea, isn't it? You know, planes flying this way, you want to shoot it down. We make friends, not enemies. This way you want to shoot it down, and so you need to fire at a particular point so that you're at the same point of time. That's confusing. You get the idea. So then all you would do, you'd have IJ, and then you'd have a third one down here, K, and you'd have a third equation to solve. Hopefully this intercept idea has worked for you. It's not a difficult thing, and really the number crunching is where you make your mistakes. So get your calculator to do as much as possible, get the idea, and then just get the calculator to number crunch for you. Thanks guys, see you later.